Hello viewers, welcome to this series of lectures on spectroscopy. In this part 2 of our discussion on Raman spectroscopy, I will be talking to you about pure rotational and pure vibrational Raman spectra. The session is planned as follows. To begin with, we will recall what we did in the previous session about the basics of Raman spectroscopy. Thereafter, we will have discussion on pure rotational Raman spectrum. This will be tricked up as follows, that is, we will start with the prerequisites for such a spectrum to be observed. This will be followed by the kind of energy expression what we come across, then the selection rule. It will be followed by the kind of spectra we get and what is the implication or the significance of that spectrum. Thereafter, we will come down to pure vibrational Raman spectrum. This also will be followed in the same fashion, that is, we begin with prerequisites followed by energy expression, the selection rules, and we see the kind of nature of spectra I get there and what is the significance of that. And towards the end, we will try to sum up what we do today. Okay, so that's the way we are going to go about it. Okay, let us make a beginning by recalling what we did in the previous session. Basically, we started with making a statement of the kind that EM radiation, that is electromagnetic radiation, having wavelengths comparable to the species with which it is interacting, it gets scattered. That means, if the wavelength and the kind of dimensions of the interacting species, the atoms or the molecules happen to be comparable, then we expect scattering to come into picture. And most of the scattered light what we observe, we find has the wavelength similar to what is there on the incident radiation. That means, there is no difference in the wavelength of the radiation which is coming out as scattered light. However, a small portion of the scattered light has different wavelength. The presence of radiation of different wavelength in the scattered light is called as Raman effect. So, that is a very significant thing we learnt in the previous session, that is what is Raman effect. Then another thing which we deliberated upon was that this radiation, when we try to kind of give a quantum mechanical interpretation to this observation, we realize that the radiation photon, when it interacts with the molecules, it can undergo either elastic or inelastic collisions. And when these kind of collisions happen, the ones which are elastic in nature, that is when you have got elastic collision between the photon and the molecules, there is no energy exchange, and this leads to Rayleigh scattering, that is the scattering at the same wavelength as the incident radiation. And in the cases when there is an energy exchange, that means, when the collision between the photon and the molecule happens to be inelastic, in such a case there will be energy exchange, and that energy exchange can bring in some kind of a rotational or vibrational excitation in the molecule, or it can lead to rotational or vibrational relaxation, and that is what basically is our Raman effect. And then as we mentioned earlier too, that Raman effect basically is a consequence of inelastic scattering of the photons by atoms and molecules. So, that is broadly what we did in the previous session. Now let us start with talking about pure rotational Raman spectrum. How do we go about it is, that is, we know, we will recall from our earlier understanding when we talked in details about a rotational spectrum, we know that the rotational motion of molecules is quantized. We talked about rotational motion in terms of a rigid rotor followed by non-rigid rotor, and we know the kind of energy levels we get there. And the quantized energy levels of a rotating molecule are given by the following expression, which happens to be E j to be equal to B j into j plus 1 minus D j square j plus 1 square, where B happens to be the rotational constant, j happens to be the rotational quantum number, which can have a value of 0, 1, 2 and so on and so forth, and D happens to be a centrifugal distortion constant, and this magnitude of D is much smaller than that of B. Okay. So, that is the kind of expression we had, and that this term, the second term, the negative term here comes because of the non-rigidity of the molecule. That is what we learned in case of rotational spectrum. Now, in the context of Raman spectrum, we can ignore the centrifugal distortion constant, because this happens to be very small in magnitude, and as a consequence of that, our operative energy expression becomes just this, that is E j to be equal to B into j plus 1. That is, where j happens to be again 0, 1, 2 and so on and so forth. And the selection rule now in the context of Raman spectrum is delta j is equal to 0 or plus minus 2. That means, either there is no change in the rotational energy level or it can change by 2 units, either it gets excited or gets relaxed by 2 units over there. Now, you should contrast this with what we had in case of microwave spectroscopy. When we talked about a rotational spectrum, we know that in that case our delta j happened to be plus minus 1, that is the rotational energy level could change only by 1 unit, whereas in case of Raman spectrum we have it changing by 2 units. It is a very significant observation here. So, we have got that there are energy levels there, the energy expression we learnt about, we will come to energy levels later on. Now, what is the prerequisite for such an interaction to take place? That means, what is the requirement in the molecule so that it can show our rotational Raman spectrum? And you recall that we did make a mention in the previous session also, that is the molecule must be anisotropically polarizable. Let us have a revisit this. What basically it means is that if I have a molecule and if I apply some kind of a electrical potential to that, so the molecule gets polarized, and if it gets polarized to different extents, if I apply potential in different directions, then it is said to be anisotropically polarizable. That means, the polarizability is different in different directions. Normally, when you talk about polarizability of a molecule, it is represented in terms of a polarizability ellipsoid. Let us see what it is. A polarizability ellipsoid is basically a 3-dimensional surface whose distance from the electrical center of the molecule is proportional to 1 by square root of alpha I, where alpha I happens to be the polarizability. That means, if along a given direction the polarizability is more, then the ellipsoid will have a shorter dimensions there. If polarizability is less, ellipsoid will be larger. Okay. Now, that is, as I just mentioned, alpha I happens to be the polarizability along the line joining a point I in the ellipsoid with the electrical center. That means, if I have a molecule, the molecule has an electrical center. From this center to the ellipsoid, so if I have any point on the ellipsoid, so this distance is what is going to be determined by the magnitude of polarizability along this direction. Okay. So, that is the way we generate polarizability ellipsoid. So, having learnt about the prerequisite for the interaction, prerequisite to observe rotational Raman spectrum, let us see that if I make a radiation interact with the molecule to measure the rotational Raman spectrum, what kind of spectra do I get there? Now, we know that our selection rule is delta j is equal to 0 and plus minus 2. If in such a case the transition corresponding to delta j is equal to 0, that implies that there is an elastic collision between the incident photon and the molecule, and this will give rise to Rayleigh scattering. That means, there is no energy exchange, because delta j is not changing, means there is no energy either absorption or emission over there. Okay. So, this will lead to Rayleigh scattering, and the signal will be observed at the excitation frequency. That means, whatever frequency I use, you remember that we normally use lasers for the purpose there. So, the scattering will be at the same frequency as that of the incident radiation there. So, let us move further and see that how do we get the Raman scattering. Raman scattering will come into picture, we will observe Raman scattering when our second part of the selection rule comes operative, that is delta j happens to be plus minus 2. When delta j is equal to plus 2, what will happen is the molecule will gain energy from the photon, and the signal which will come will lie on the lower wave number side of the excitation radiation, that is, this will give me Stokes lines. On the other hand, when delta j is equal to minus 2, that means the molecule to begin with is an higher energy level, it is coming down to lower energy level, that means the molecule is losing energy. That means, the molecule loses energy to the photon and the signal will lie down to the side which is a higher wave number side of the exciting radiation. This will be my anti-Stokes lines there. Let us see it pictorially. What you see here is the energy level diagram for a rotating molecule. So, what you have is there are different quantum numbers there, j is equal to 0, 1, 2 and so on and so forth, and the energy increases accordingly. Now, what I am trying to show here is that there are two sets of transitions possible here, one which correspond to delta j is equal to plus 2, that means you go from a lower level to higher level, the molecule is gaining energy. So, when you have got transition, say the first transition will be from J is equal to 0 to 2 or maybe 1 to 3 or 2 to 4 and so on and so forth. So, all these transitions will be accompanied by excitation of the molecule. That means, they will be taking energy from the photon. In other words, it will mean the photon will come out with lower energy, means it will be having lower wave number. On the other hand, in the transitions which accompany a kind of a change in quantum number by -2, that is from J to J minus 2, that delta J is equal to -2. When that happens, then what will happen is the molecule to begin with is in higher level, it is coming down to lower level. So, the molecule is losing energy, giving it to photon, the photon will be of higher energy, and this will lead to signals which will be having wave number greater than that of the incident radiation. So, that will give me the anti-Stokes lines there. So, this will give me Stokes lines, this will give me anti-Stokes lines. Let us look at a spectrum. The spectrum will be something like this, because in the center we will be getting an intense Rayleigh line. This is because of our elastic collision, that means there is no exchange of energy. So, the signal is coming at the same frequency as that of the incident radiation there. On the other hand, on this side, the lower wave number side, I get series of lines which are called as Stokes lines, and on the other side I am getting anti-Stokes line there. But that is a kind of spectrum here. So, just have a look at the note, take a note of the position of the lines here. So, the lines here are, the first line is coming at about 6B from this radiation, and then at 10B, 14B and so on and so forth. On this side also it is, the first line is coming at 6B, then 10, 14, 18 and so on and so forth. That means, the first lines come at a distance of about 6B, then all subsequent lines will have a separation of 4B. So, that is the kind of spectrum I am getting. Let us try to see what are salient features of this spectrum here. So, as I just mentioned, the first line from the excitation wavelength or the frequency or the wave number will be located at 6B, whereas the subsequent lines are at a distance of 4B each. Secondly, the intensity of Stokes lines and anti-Stokes lines are comparable. This is very important here. When you do rotational Raman spectrum, we find that the Stokes lines and anti-Stokes lines have got comparable intensity. The reason for that is because this signals are coming because of the first few rotational energy levels which are reasonably populated. So, whether the transition goes upwards or downwards, so they will be reasonably intense. We will find that when we talk about the vibrational Raman spectrum, this will not be true, because the things are different here. We will come to that later. Now, let us try to see what kind of energy expressions we have. Suppose I am talking about delta J is equal to +2 kind of a change, then the change in energy can be given as Ej plus 2 minus Ej, that means J plus 2th level minus this energy. That gives me an expression. I just substitute the energy expression we had, general expression earlier. Substitute that here, we find that this comes out to be at B into 4J plus 6 centimeter inverse, where the signals will be located at new excitation minus this B 4J plus 6 centimeter inverse, where J happens to be 0, 1, 2, because when we say delta J is equal to +2, our first transition will be from 0 level. So, 0 to 1, 2 and so on and so forth. So, if I just substitute the value of J here as 0, 1, 2, I get the position of each one of the lines there. If I put J is equal to 0, I get 6B. Put J is equal to 1, I get 10B and so on and so forth. That is how I get an expression for the location of each of the Stokes lines in this case. Similarly, I can do an exercise for anti-Stokes lines. What I will find is that will be, that is energy of Jth level minus J minus 2th level. If I do that, it will come out to be B times 4J minus 2. Now, where J will be having value of 2, 3, 4, because the first kind of transition in the anti-Stokes lines will start from J is equal to 2 level, because from J is equal to 2 to 0 only, that is the first transition we have. You can't have a transition from 1. Okay. So, first transition will start from 2 and so on and so forth, and the location will be the excitation wavelength, excitation wave number plus B times 4J minus 2. Substitute the value of J, you get the location there. Put J is equal to 2, so this is 8 minus 2 is 6, it will be 6B. Put J is equal to 3, it will be 10B and so on and so forth. So, that gives us expressions for locating the signals in the spectrum here. Alternatively, we can do the location of spectral lines with the following expression, where nu happens to be nu bar excitation plus minus b 4j plus 6 centimeter inverse. But in this case, we have got some specifications to be clarified here, that is j is the rotational quantum number of the lower energy level. That means, whether I am talking about excitation or emission, in both the cases I have to take j to be the one which is lower in number, and plus sign will give me anti-Stokes lines and minus sign will give me Stokes lines. We can just work it out, it will come out to be same what we had earlier. So, that is an alternative way of locating the signals in the rotational Raman spectrum. Now, let us see what is the significance of this spectrum I have got. The significance is, if I have got a resolved spectrum, so which happens in the case of small molecules, we do get a resolved spectrum. This will provide us the value of B, because we know that the first line is at 6 B and then 10 B and so on and so forth. If I can locate them, I can get the value of B, which will give me readily the moment of inertia, because we know that B and I are related, which in turn is going to provide me the bond length, because we know that I is equal to mu r square. So, if I know I can get the value of r. So, that means in principle the rotational Raman spectrum can give me a means of getting the bond length of simple molecules. Second significance, very significant observation here is, normally the homonuclear diatomic molecules do not have any dipole moment. Say molecule like hydrogen, nitrogen, oxygen, for such molecules I just cannot measure their bond lengths with the help of rotational spectrum, just rotational spectrum, because for rotational spectrum to be observed, the molecule must have a permanent dipole moment. So, since they do not have dipole moment, they will not be observed over there, but the Raman spectrum will provide the desired information, because that is kind of substituting for that information which we can't get from rotational spectrum, I can get from rotational Raman spectrum. So, that is one significant contribution of rotational Raman spectrum. Thirdly, if the molecule happens to be large or heavy, the moment of inertia is large obviously. So, what will happen is the rotational constant will be very small and the spectra will not be resolved. That is a general observation we can make about rotational Raman spectrum. Let us quickly take an example here. So, the rotational constant for nitrogen molecule happens to be 1.99 centimeter inverse. So, our issue is to calculate the frequencies of the first Stokes line and the second anti-Stokes line when measured using a laser having a frequency of 336.732 nanometer. Now, how do I go about it? How do I go about it is, the strategy will be as follows. First, I will have to compute the excitation frequency, that means this is the wavelength of the laser given to me. So, I need to know what is the excitation frequency, that is the first step. Thereafter, I can compute or calculate the frequencies of the desired Raman lines, whether the Stokes lines or the anti-Stokes lines. Let us see, we will do it and see it here. Let us start by computing the excitation frequency, and before I proceed, I would like to make a mention here that whenever we talk about rotational spectrum, vibration spectrum or rotational Raman spectrum, typically we use the term frequency, whereby whereas actually we mean wave number, because that is a very convenient term to be used over there. So, whenever we talk about frequency, we should be clear that we are talking about wave number in this case. Okay. Now, we know that the wave number is related to wavelength as nu bar is equal to 1 by lambda. We are given that the lambda happens to be 336.732 nanometers. So, we can just convert it into centimeters. So, then we just substitute it in the formula and get the value of our frequency, and that happens to be 29697.2 centimeter inverse. Okay. Now, the second step was to compute the Raman lines. The first requirement we had was to find the location of first Stokes line. Now, we know that the location of Stokes lines is given by the following expression, we just talked about it some time back, that is, it is equal to the nu incident or excitation frequency minus B times 4j plus 6, where j happens to be 0, 1, 2 and so on and so forth. Since my objective is to locate the first Stokes line, essentially first Stokes line will come when j happens to be 0. I substitute that over here, and what do I get? I just substitute the values of excitation frequency and rotational constant B and the quantum number over there, I get the value to be 29685.3 centimeter inverse. So, I know where I am going to get my first Stokes line. So, the second thing which we wanted to compute was the location of second anti-Stokes lines, and we know that the location of anti-Stokes lines is given by the following expression, which happens to be new excitation plus B times 4j minus 2, where j happens to be 2, 3, 4 and so on and so forth. Now, since we need to locate the second anti-Stokes lines, so the value of j will be 3, the first will be from j is equal to 2 and so on and so forth. So, what we do is we substitute the value of B, j, and what we get is the value for the location of second anti-Stokes lines, that happens to be 29717.1 centimeter inverse. So, we see that how simple the expressions are, and we are able to predict a reasonably good location for the expected spectrum for the molecule. Let us move on to pure vibrational Raman spectrum. We know that the vibration motion of molecule is quantized. This we talked in detail earlier, and the quantized vibration energy levels are given by the following expression, which again is very familiar to you, that EV to be equal to V plus half omega E minus V plus half square omega E XE, where omega E V happens to be the vibrational quantum number having value of 0, 1, 2 and so on and so forth. Omega E is the equilibrium vibration frequency and XE is the anharmonicity constant. We talked in detail about that in the vibration spectrum. Now, the selection rule happens to be delta V to be equal to plus minus 1, plus minus 2 and plus minus 3, so on and so forth. So, that means all possibilities are there. Now, if I look at the possible vibrational transitions, so as per the selection rule, what you find is that there can be a large number of transitions possible over there, because when we have delta V to be plus minus 1, plus minus 2, plus minus 3 and so on and so forth, you can go from practically any level to any other level. So, you expect a large number of lines, signals over there, whereas what normally are observed are only a few. The reason for that is because only what you observe here is the fundamental, that means from 0 to 1 transition, the first overtone from 0 to 2 and second overtone from 0 to 3. The reason for this is that the transitional probability of delta V to be equal to plus minus 2, plus minus 3 and so on and so forth, this decreases very rapidly. And secondly, the population of levels from V is equal to 1 onward is very low. So, we do not expect many transitions to originate from V is equal to 1, 2, 3 and so on and so forth level. And secondly, any transitions which involve larger changes in delta V are going to be of very low transitional probability, means intensity is going to be negligible over there, we will not be observing them. Okay. So, with that let us try to see where are these located. The fundamental is from V is equal to 0 to 1, we substitute the expression there, we find it comes out at omega E 1 minus 2 XC, that is the location of my fundamental. You remember that we have done all that in the vibration spectrum in details. The first overtone will be from V is equal to 0 to 2, that will be located at 2 omega E 1 minus 3 XC. And hot bands, we talked about the bands which are observed when you increase temperature. When you increase temperature, V is equal to 1 level becomes reasonably populated, and we do expect some transitions from V is equal to 1 to V is equal to 2. Such bands are called as hot bands, and that will be located at omega E 1 minus 4 XC. So, they are the possible locations of these transitions to be there. But when you come to Raman spectrum, vibration Raman spectrum, we find that delta V happens to be 0, plus minus 1, plus minus 2, so on and so forth. But let us see what does it mean. What does it mean is that when we have delta V to be equal to 0, means there is no exchange of energy between photon and the molecule. This will give rise to a Rayleigh's line, which will be located at the same frequency as that of the incident frequency. Secondly, as regards the Raman lines, though we just said that there are different possibilities are there, fundamental, first overtone, second overtone, but in the context of Raman lines or Raman spectrum, we observe only fundamentals. The other signals, that means first overtone, second overtone, normally are not observed, because they happen to be too weak to be observed, but they are there sometimes, but normally we do not come across them. So, essentially these signals which are the fundamentals ones, they will be located on both sides of the incident frequency, that means there will be Stokes lines, there will be anti-Stokes lines like that, and that will be the location will be new excitation plus minus omega e 1 minus 2 x e, because that is the location of my fundamental there. This is the location of fundamental. So, this is my incident radiation. So, either it will be plus or minus. So, you are getting either anti-Stokes lines or Stokes lines there. So, the effective selection rule now which comes out for our vibration Raman spectrum is just that delta V to be equal to 0 and plus minus 1, 0 for Rayleigh scattering and plus minus 1 for the Raman scattering. Now, before we proceed further, let us just quickly look at the prerequisite to observe vibrational Raman spectrum. We have just seen, okay, if the interaction takes place, where do I expect the signals to be there, but will the interaction take place or not? So, what is the prerequisite for that? And we have been talking about it. We just talked some time back in the context of rotational Raman spectrum that the polarizability must change during the course of a rotation. Now, in the case of vibration Raman spectrum, the requirement is the vibration should be accompanied by a change. The change could be in the size, direction or the shape of the polarizability ellipsoid. Let us take one simple example here. I am talking about the symmetric stretching mode of vibration of water. Now, what we find is in the center this is a normal water molecule and this is the corresponding polarizability ellipsoid here, and this tells me if what will happen to polarizability ellipsoid when the molecule gets stretched out. That means, if you are stretching it out, when you stretch out you see that these bonds have become longer. When they become longer, the polarizability becomes more. When the polarizability becomes more, the polarizability ellipsoid becomes, it shrinks, it becomes smaller in size. On the other hand, when you got contraction, that means these bonds have become smaller now, the electrons are closer to the nucleus, nucleus has a lot of influence on that, the polarizability decreases. The polarizability decreases, my ellipsoid becomes larger. So, what you find is that in this simple case, you have water molecule, it is undergoing stretching vibration, symmetric stretching vibration. So, in this case there is a change in the size of the polarizability ellipsoid. So, this mode of vibration is going to be Raman active. So, or it will going to be vibration Raman activity. So, that means I will be seeing this mode of vibration in the Raman spectrum if I perform the experiment over there. Let us take an example. Let us have a look at the vibration Raman spectrum for carbon tetrachloride, which was measured by using a 488 nanometer laser source. So, what you see here is that at a frequency 20492 centimeter inverse, which corresponds to 488 nanometer, we got a very intense line which happens to be the Rayleigh scattering when delta V to be equal to 0. And on the lower wave number side we got Stokes lines, on the higher wave number side we got anti-Stokes lines there. So, there are two sets of lines over here. You see that this spectrum looks slightly different from what we had in case of rotational Raman spectrum. In that case the intensities of the Stokes lines and anti-Stokes lines were comparable, whereas now they are different. Let us take up the salient features of vibration Raman spectrum we have just seen. The first one is that the Stokes and anti-Stokes lines are equidistant from the Rayleigh line. That is what we actually expect to observe. Secondly, the Stokes lines are much more intense as compared to the anti-Stokes lines. You can contrast it to the rotational Raman spectrum, because in that case what we had was the two were of roughly of similar intensity. So, having discussed rotational Raman spectrum and vibrational Raman spectrum in reasonable details, let us try to now sum up what we did today. What we did today was that we reviewed the contents of the previous session, where we recalled what we did earlier. Thereafter, we discussed the origin and significance of pure rotational Raman spectrum in terms of the prerequisites, the energy expression, the selection rule, the nature and significance of spectrum, and thereafter we took up the discussion on origin and significance of pure vibration Raman spectrum, again in terms of the prerequisites, the energy expression, the selection rules and nature and significance of the spectrum. And then of course, we did mention about the salient features of the spectra we get there. So, with this we come to the conclusion of our discussion on Raman spectroscopy. In the next session we will take up electronic spectroscopy, wherein we will talk about what is electronic spectrum and then what kind of information we get from there, and so on and so